someone read some of the arguments for company A that we've got over there? Yeah, read them. You guys are close. You got front row seats. Okay, on average, less late. So what do you mean by average? What measures were you looking at? Mean? Okay. And did anyone cite any other measures? The mode? Anyone else? The median? So all the M's, the mean, median, and mode, they were all what? Lower. So that means that overall, the wait times were shorter for company A. Okay. What about for company B? Okay, I heard consistent. I see consistent in their lateness. Were any of the company B ones like super late?
If they're all late, that means they're not late.
Okay. So you're probably going to wait, but are you going to wait as much? Okay. Okay. So I see lower range and lower IQR. I see more predictable, more consistent, more accurate. Getting there about the same time, only 1 to 6 minutes late. Okay, I think you guys like grasped this pretty well. So if you look, what do all the arguments for company A center around? The measures of what? Okay, so is that spread or central tendency? Yeah, so the arguments for A center around the central tendency, and what do the arguments for B focus on? The spread. Okay, interesting. All right. Cool. Let's calculate some standard deviation, guys. You guys remember doing this in Algebra 1? Okay, in Algebra 1, we made... Okay, take a moment to think about how important it is to know the variability of wait times. Based on the data we have about delivery times for company A and B, is it enough to just know their mean or median wait times to compare them? Why or why not? We kind of addressed this, but we're just going to bring it home right now. Is it enough to only talk about the mean, median, and mode? Or are there other factors that we need to consider? Other factors, right? Okay. So we're going to talk specifically about one of those other factors today. So in Algebra 1, we learned 3 measures of central tendency. We've already talked about those in this course, mean, median, and mode. And then also last year in Algebra 1, you talked about 3 measures of spread. The range, okay, that's your max minus your min. Your IQR, that's your third quartile minus your first quartile. And then the last one was standard deviation. Okay, and we used a formula for that last year. This year we're going to do it more in steps. And we're going to break down what each of the steps means and go more involved in it, okay? This is another measure of spread. Like the range, like the IQR. Okay, consider our dot plot for wait times for company A at the right. Here you can see that the mean 2.15 is shown as a vertical red line. Okay, so if these were pennies on a ruler, this is where your finger would have to be. Everybody remember doing that? Yep. Thanks. Okay. What do you notice? Would you say that the wait times are typically close to the mean wait time or typically far away from the mean time, and how can you tell? So you're writing your observations. I'm not going to write anything, but I can help you guys think it out. So are they close to that red line or far away? I don't know that there's a totally right or totally wrong answer to this. Does anybody have any ideas they want to share out? Or like a gut feeling? Okay, it's skewed right.
I think it looks symmetrical. I think it looks symmetrical.
Well, we made a box plot. Was it symmetrical? We had a long whisker on the right, right? Whoops, I guess I wasn't recording. Sorry. Sorry. I don't know. Okay, we're finding the deviations for each of these by subtracting the mean, which was 2.15 from the wait time. Okay, so the mean is always going to be the second number, the one that we're subtracting. So just be careful. I'm not going to write that out every single time. Okay, so you can probably do this on your calculator. I'm going to pause this video because right now it's probably like watching paint dry. Filled in-ish. You have this whole thing filled in. Okay, number 4 says, what do you think would happen if you were to use the average of the deviations to try and find an average distance from your mean? That should be a little X bar on the blank. So if we added these all up and then divided by how many there are, I think there's 20, what would we get? What would we get? Okay, I'm going to make you do it. I want you to add all these up. I'll do it with you. I'm feeling fun. I'm feeling fun. Okay. So I've got negative 5.15 plus negative 1.15 plus. Yeah, I'm recording. I'm doing this whole thing. Negative 0.15 plus 1.85. I should hear all kinds of calculators going behind me.
I'll work that.
Whoops, that's a negative 4. I'm doing great. I'm almost halfway done.
Second number. Zero. Good. Is zero? Yeah.
Okay.
Okay, you guys are distracting me, and I'm trying to do this for the video and get the right answer. Okay. Moment of truth. I hope I did it right. Oh! So, can we add them all up and divide by how many there are to get an average distance?
Yes.
What's 0 divided by 20?
0.
Are they on average 0 units away? No, that doesn't make any sense. Okay. Okay, yeah, they're not all right on top of each other. Okay, so put that in your own words. Why can't we add them all up and divide by 20? In the little box, in the little speech bubble box. Number 4. X bar. If we add them all up to divide by 20, what do we get? Does that work? Remember that deviations are different than distance, right? Distance is always positive, and deviations have positive or negative signs. What did we get? What did you get on your calculator? So if I do divide that by 20, I still get 0, right? It doesn't work. All right, so let's brainstorm. What ideas do you have for correcting this problem?
No negatives.
No negatives. How do we get rid of negatives?
Absolutely.
Okay, that's actually a way. One way is that instead of using the deviations, we use the absolute value of the deviations, and that actually has a name. It's called the absolute deviation, and it is a statistical method, but it's not the one we're going to use, but that's a really good idea. Anyone else have any ideas? Do you remember what that crazy formula looks like that we did in algebra?
Oh,
Isn't it a squared minus 4ac?
quadratic formula.
It kind of looks like the quadratic formula a little bit because it has a what in it? It has a square root in it. Okay, so
Yeah.
what do you think we had to do to get rid of negatives? It has to do with square root, kind of. What happens if you multiply a positive times a positive? Okay, stays positive. What happens if you multiply a negative times a negative? So what can we do to these deviations to get them to change signs and stay all be positive? Okay, this is painful.
What was the question?
Okay, we have one idea on the table, which is a valid idea. It's an actual statistical method. It's called absolute deviation, where we use the absolute value from the mean. Okay, but I'm telling you that that's not the preferred method for statisticians. Okay? What did we have to do in the formula under the radical sign? You guys remember? Yeah, and then do what? Say again? I thought I heard it. Square it. If you square something, it's always positive, right? Okay. So, if we're squaring something, that's going to get rid of those negative signs. Okay? What? What's a negative times a negative?
Well, positive, yeah.
Okay.
It's law.
Okay. Go down to this box over here. One reason that statisticians prefer standard deviation is that squaring our non-zero deviations makes those deviations that are between -1 and 1 smaller, while making those deviations that are less than -1, those deviations that are either less than -1 or greater than 1 get bigger. Reducing smaller deviations and magnifying greater deviations provides a better perspective on variability. Okay, let me explain what that means. If I have a number between -1 and +1, like -1/2, and I square it, what do I get? +1/4. Okay, very good. Do you see that that's actually a smaller distance than 1/2? So anything that's between -1 and 0, it's actually going to give us a smaller quantity. Okay? And then if I square something that's like -10, I'm going to get 100. So I'm magnifying the greater distances and reducing the smaller distances. And that's why statisticians prefer this method. Is that okay with everybody? Yeah. Okay, perfect. Why that makes a difference is beyond the scope of this course. So the ideas that we had for correcting this problem were absolute deviation, like taking the absolute value of the deviations and then squaring the deviations. Okay, so write those down. To complete the table by calculating the squared deviations. Okay, so that's what goes in this final column. I didn't want to give away that it was squaring, so I didn't put anything in here. We're writing squared deviations in here. Okay, so whatever this deviation is, you're going to square it. Now watch. If I take -5.15 and I square it, what's going to happen? Look at it. What's wrong with the sign? It's still negative because I didn't put what around it? Parentheses. So you either have to remember to put the parentheses around it, or you just know, hey, they're all going to be positive because if I square a negative, I get a positive. Right? You see what I'm saying?
Yeah.
Okay, go. Use your calculator.
Do you want us to do all the decimals?
So on this one, you've got 2 decimal places. On the squared deviations, I want 4 decimal places. Okay, you'll be fine. You'll live. So we've got them all written down, all of our squared deviations. What do you think we're supposed to do now? Yeah, we're going to add them all up. So we're going to add up all of them. Go ahead and add those all up in your calculator. I'm not going to write it down. You're going to have to do it. Sorry, not sorry. Huh?
Oh gosh. Is there anyone who's done already that wants to use the water?
Okay. 188.55. Okay. Now, what does it say? It says, what are the units for the mean and the deviations in the table above?
Minutes?
Minutes. Both of them?
Yeah.
Okay. Okay, take a minute to think about why they are the same. Yeah.
Because they're both in it's time, and both of the times were measured in minutes.
Yeah, the deviations are a difference of minutes. So if I take 2.15 minutes, and if I take 5 minutes and subtract 2.15 minutes, I'm going to get minutes because it's a difference of minutes, right? Okay. Okay, perfect. Flip to the next page. Why did we square our deviations from the mean?
So we didn't have negatives.
Correct, to get rid of the negatives. Write that down. Now, if the deviations were in minutes, which is what you guys just told me, what happens when we square the deviations? What are those units? Minutes what? Minutes squared. Okay, are they the same or different from the units for the deviations? If one is minutes and one is minutes squared, that's obviously different, right? Okay, in box 11, in the table below, on the table on the other page, find the mean of the squared deviations. So, we have our squared deviations. We already added them all up and found the total. What do we still have to do to find an average? Divide by 20. Divide by how many there are, right? Okay, so we take our 188.55 and we have to divide by 20 because we had 20 values.
9.4375.
Okay. Okay, guys, this actually has a name. The mean of our squared deviations is called the variance, and it has a symbol. It's like with the little hat, and then it's squared. Okay, it's called sigma squared. Yes, we'll talk about that in a minute. All right, we'll pause here.